Okay. So I'll talk to you today about potential inhomogeneities in presence of strong interactions, and we will see what that leads, specifically focusing on what that does to superconductors. And you'll see the answer is not different depending on different situations. In one case, we will see that this leads to superconductivity in a system, whereas in other cases, we will see that is of course tries to kill superconductivity in various systems. So to start with, this is part 2 of, this is actually 2 different works, but they have a common theme. So the parts of superconductor is done with my student Abhishek Samanta in TIFR, and the data superconductor part will be work done with Amit Toshad, who is a professor in IIT Kolkata, and a student Devmata Chakravarti. So let's start from what we know about metals, the simplest things. These are well described by almost non-interacting electrons. So you take the lattice, you make all the bands, and then you fill up the Fermi sea. And your low energy excitations are basically small particle excitations around the Fermi surface. Okay. Now if you have real materials, you have more complicated bands. This is just copper, which is MCC lattice, and the Fermi surface might look that complicated. This is a picture of the Fermi surface in the momentum space. This is how the band dispersion looks like. So there's a lot of complication in getting the correct bands and so on. But once you have got them, it's still non-interacting physics. You fill it up to the Fermi level, and yeah. So all the complication lies in finding where the Fermi surface is. But once you have that, it's basically the same physics around Fermi surface that you get for free electrons. Now you can ask, why does this happen? Well, electrons have Coulomb interactions, and the answer was given by Landau, which is that near Fermi surface, you have the fact that electrons are fermions, so they have Pauli exclusion working for them. And near Fermi surface, the excitation energy goes linearly with the momentum deviation from the Fermi wave vector, whereas the Pauli exclusion shows that the width of the excitations or the decay rates would go as k minus kf whole square. At least in 3D, this is exactly how it goes. So which means that as you go close towards Fermi surface, you have almost particle-like excitations. Okay, these have charge E, spin half, and then you can try to make a weakly interacting theory of this almost particle-like excitations or quasi-particles, and this leads to quantitative changes from a theory that you would have calculated with free electrons. Okay? For example, in a free electron theory, you know that the specific heat goes linearly with temperature with some coefficient. If you have Landau Fermi liquid theory, it again goes linearly with temperature with a different coefficient m star. So quantitative changes come into picture, but qualitatively the picture is the same as, essentially the same as free electron gas. So that's why metals are essentially well described by free electron gas. If we are talking about charge transport, the other thing that can happen is superconductivity, which was discovered by Cameron Owens in 1911, where at a finite temperature, the DC resistivity suddenly drops to 0. Okay? Good. Now, this took about almost 40 years to be explained. It was explained by Bardeen, Cooper, and Schrieffer in 1956. That what happens is that the electrons somehow feel attractive interaction with each other. And when that happens, in presence of a field Fermi C, the electrons form bound states. They're called Cooper pairs, total momentum 0, net spin 0, with a binding energy which is actually a non-perturbative function of the coupling constant. But then, since the electrons are bound, the single particle excitations are gapped. But the pairs which have some bosonic characteristics can form a BC of Cooper pairs, and this leads to dissipationless flow of charge. This is nothing but superconductivity. So, a couple of things came out of this theory. For example, The superconductivity is lost when you have raised the temperature to the order of binding energy, when bound Cooper pairs lose their meaning, which also means that Tc is related to the gap, single particle fermionic gap, at zero temperature, at least for S-wave superconductor. There is a particular number, 3.52, etc. Now I started by saying that there are attractive interactions between electrons. Now this can come due to various reasons. This could be phonons, this could be spin fluctuations. If you have cold atoms, this could be Van der Waals interactions, and so on and so forth. But as long as you have an attractive interaction, then the BCS theory kind of tells you what is going to happen. Okay? More interesting things, however, have started happening when electrons are almost localized, or they are all close to some insulating limit. Okay? So this is what we talked about is metals, and then superconductors form out of a metallic normal state. But more interesting thing happen when electrons are close to being insulating. So how can you make electrons insulating? Well, the simplest thing you do is you can just put them in a lattice and you fill them up right up to the point where the one bands are occupied and other bands are empty. Then you have band gaps. And one way to think of band gaps is that you do not have any propagating wave-like states there. So if you try to put something with an energy there, it will get localized, it will remain close to the surface, and so on and so forth. So fermions can be localized by periodic potentials, band insulators. This is something you're familiar from textbooks. Fermions can be localized by broken symmetry. For example, you can take a square lattice and put one electron per site on that lattice. This is a metal because it has filled up half. I mean, each site can in principle have two electrons. You have put one on each side. So it's a half-filled band. So it's essentially going to be a metal. However, if by chance, due to interactions, you introduce antiferromagnetism in the material, which means that spins try to prefer one sublattice than the other. So let's say up, down, kind of an ordering. Then the unit cell is changed. And in the new unit cell, this object is the full Brillouin zone, which is called the magnetic Brillouin zone. And then within this magnetic Brillouin zone, the band is completely filled, and then you can basically apply a theory of band insulators to this modified band. And so you can formulate this in momentum space or real space. You remember that the filling of fermions is important here, but these are two very simple ways you can make insulating states.
So why do you call it Slater insulator?
Okay, so because okay, this is more or less historic. The Slater insulator, because it's originally studied by Slater, and one way of writing it, which he used at that point, is if your band is completely filled, you can write it either as occupying all the momentum states, or equivalently occupying all the real space orbital states. And he made a Slater determinant out of this. So that's the other description of the Slater insulators.
So what's the difference with Mott insulator?
Coming. Okay, so technically a Mott insulator would happen without any broken symmetry.
Okay.
But we all know when Mott insulators happen, this also breaks symmetry, the spin symmetry. We will come to that in a minute.
Does a Mott insulator have a band gap if there is no broken symmetry?
It should, because even, so for example, if you take actual high Tc compounds, and you look at the charge gap as measured from the resistivity data, you will get a number of the order of electron volts. Whereas you do neutron, which you know is going to give you the spin-spin interaction, which is related to the antiferromagnetic scale, that's like 100 millielectron volts, 150 millielectron volts. Okay, so there's a huge difference between, okay, this goes back to the old question of at any finite temperature can you define an insulator and so on, but we operationally can define an insulator because we can define a charge gap from the resistivity data. And that would have nothing to do with the spin gap, which is going to be governed by some different scale there. Okay, so that's, but there's more. You can do random potentials, disorder. It can be localized by strong random potentials. So what you have here is one realization of a disorder potential on a square lattice, and these are the lowest 5 eigenstates drawn by diagonalizing that whole problem. And you can see that they are very localized in real space. They don't overlap with each other much, and hence the charge motion is forbidden by the lack of overlap between these localized eigenstates. In 3D, you will basically have localized states mixing with some extended states in the between, whereas in if you have strong disorder in 3D and any disorder in 1 and 2D, all states become localized for the fermions. And you can see something similar as you increase disorder. What you see here is one data from very recent data where you can see that things start going from metallic to being insulators as you change the disorder strength in the system. So we have learned that we can create insulators by potential. We can create insulators by breaking symmetry. We can create insulators by putting a lot of disorder. And now coming to the last one, which is fermions can be localized by strong repulsive interactions, which is called Mott insulators. And the easiest way to see this is to look at a particular model. Think about electrons hopping on a square lattice and paying a huge repulsive energy cost when two electrons are sitting on top of each other. Basically, anytime they come close together, they just pay a huge repulsive cost u, and u is much larger than t. So if u equal to 0, you just get back to my old metallic argument that you should have a metal. If u goes to infinity, you cannot think of this problem in momentum space. You have to think it in real space picture. And in real space, you start by saying, what is the local Hilbert space? What are the states on each side? It's whole, up, down, or up, down. And if u is large, you would say that, okay, these guys are not allowed. So you should go into some kind of a projected subspace where there are no double occupancy in the low energy energy states. Okay, so now you can see if there are no double occupancies and you have exactly one particle per site, you cannot move, because to move you have to create a double occupancy. You try to move anything, you will put two of them on the same site. So these are frozen in real space because you cannot go access these high energy states. This is called a Mott insulator. The example, as I was telling, that if you look at parent compounds of high TC superconductors, and if you just do basic chemistry, it should be metallic by valence count. But if you look at very low doping and look at resistivity data, you see that it shows insulating behavior. This is very close to one particle per site. It has an insulator with a gap 3 eV, and this is what I was saying, that the spin scale where you have antiferromagnetism is about 150 MeV, which is very different from this. And however, if you now change the filling, then this shows a number of phases. There is antiferromagnetic insulator at half filling, one particle per site. As you are going away from that, you are giving less and less electrons. You get a superconducting state which shows very non-BCS type feature. You get all sorts of states in the normal phase which we don't understand well. It's kind of the most famous unsolved problem in condensed matter physics. Okay, so till now, with all of this, what have you learned? You've learned that fermions on a lattice can be localized by potentials, which can be either periodic or random. This is the potential inhomogeneity part was going to talk about. And it can also be localized by strong interactions. Now, interesting transport happens when small charge fluctuations are introduced around these Mott insulators. If you go a little bit away, you suddenly get a superconductor. Okay, so very interesting things happen there. So the question that we want to ask is, what happens when both of these effects, both potentials and strong interactions, are present in the system? And by potentials, I mean a periodic potential or a random potential, and this will be two different cases. So the basic question that you can ask is, do these guys team up to localize the fermions further? Or they fight with each other and somehow they delocalize the fermions? Okay, that's the basic question that you can ask about a situation where both potentials and strong interactions are present. But to do this, we need a formalism to treat strong potentials and strong interactions on the same footing. You cannot say, I will first deal with the strong interactions, and then I'll put in the potential inhomogeneities later. You can't say, I will deal with the potential inhomogeneities first, and put in interactions perturbatively, because we are trying to go to a regime where both have strong influences. Okay. So to develop such a formalism, it's useful to look at what people do in usual Hubbard model when only one thing is present, only strong interactions are present. So what you do is you say that, okay, look at this guy. This is the largest energy scale in the problem. And this is a part of the Hamiltonian, which is kind of diagonal in the number basis. It just counts how many double occupancies you have. It doesn't move anything around. This guy, of course, moves things around. And you can just break it up into, so you can ask what are the possible processes? Can I draw pictures for these things? So I'm trying to move one electron from one side to another. Let's say I'm always moving an upspin electron in this case. What I can do is I can have a vacancy and then just move the vacancy back. I can have a double occupancy and then I can just push the double occupancy to the next side by moving the electron. This is called motion of doublons or holes.
So you should think of the vertical axis as time.
Yeah, so I'm just saying this goes to this. Yeah, if you vertical axis is time going downwards, if you wish. Yeah. And then there are processes where you just have up and down. You move something, you suddenly create a double occupancy. These are the processes that we said should not happen at low energy, right? And of course, it's a reverse process where you start with a double occupancy and kind of say relax it and go to a place which doesn't have double occupancies. Now you can ask what is the energy change due to these processes? And here the delta E is 0 because you have not created any double occupancies. And we are looking for energy change under H naught. And here it's U and minus U. Okay. So you can say that, look, these are very large energy change processes. These are very high energy processes. I will break up my kinetic energy into a part which is low energy processes and high energy processes. And let's not get into the technical details, but there's a way of basically eliminating all the high energy power processes by doing something called a canonical transformation. You can do it in perturbatively in T over U. And what it does actually in terms of pictures, it's much easier to understand what it does. It starts to allow second order processes where in between you had gone to some very high energy state. For example, this is a spin flip process where I have a up down, this guy hops. This is virtual, I'm not going to stay here, creates a double occupancy and comes back with a spin flip. So that gives you a spin flip kind of a term. And this leads to what is known as the famous TJ model, and people have done a bunch of work, a lot of work on high TC using this. But our goal is not to look at the Hubbard model, our goal is to look at this model. The goal is to look at the model where in addition we have a local potential. Okay, it could be random potential due to disorder, it could be some superlattice potential. Right now we are not going to specify for you what kind of VI we are talking about. Now note that what we will develop is treat this whole thing, including the potential, as your basic starting Hamiltonian. So you're going to treat both interaction and potential inhomogeneities non-perturbatively. So the only perturbative thing that is going to come about is the hopping term. Okay, so I can go back to the same processes because the actual processes are same for what possible processes of kinetic energy, except the change in energy is not 0 here. You are changing from a site I to a site j. So you're going to pay a potential energy cost equal to the difference of the potentials between I and j. Again, where it was u, you add a u plus vi minus vj, minus u goes to minus u plus vi minus vj. So I'm basically factoring in the fact that there's a potential energy cost I'm paying as I am moving my system. Now if you remember my last slide, I have to tell you that I have to first figure out what are the high energy processes, and then there is some technical way to eliminate them and get an effective low energy Hamiltonian. Okay, so now whenever I say high or low, I have to compare it with something. In the Hubbard model, it's very straightforward. U is a high energy scale, T is a low energy scale, so you compare it with T. Even here you can compare it with T, in fact some number times T, and you can say that, okay, look, if Vi minus Vj modulus is less than alpha T, alpha is a number order 1, then these guys are low energy processes. These are all high energy processes, and let me do whatever I needed to do to get rid of them. Now, you can have, on the other hand, some of the cases where this guy, let's say Vi minus Vj is of the order of minus u, and this guy is a very low energy process, and then you can say, oh, keep these terms, get rid of the others, and do the similar things here. These are called C, and then there can be a third case where none of these are low energy terms. See, U is very large, right? So you can get states where whatever you do, you don't want to hop, because either you pay interaction energy or you pay potential energy cost. So you don't want to do that. Okay.
So
yeah.
It appears there is no energy separation.
Technically, no. In fact, what we are doing right now, so right now what I gave you is something which looks like a cutoff. We are now.
So if you convince me that the results don't depend on the cutoff, then
I will do better. What we are doing right now is basically developing interpolation functions to do smoothly things and finding these interpolation functions variationally. Okay.
What's ACCB?
I'll come to that. Just these are just different cases. Yeah.
So in principle, you have to average the VIs over some random probability distribution functions.
Yeah. Right. For example, right now, what I'm saying is for each realization, what I have said it would be an operating procedure. So, for example, okay. So, David, to answer your question, ABC will be different kinds of bonds that you can think of where different things are happening. You can ask statistical distribution of this kind of bonds, and then yeah. However, it's not just the statistical distribution, is the which bond is closer to the spatial distribution also matters in some sense. So we have some ideas of how to go beyond.
So before you continue, can I play this game with binary disorder? In which case I could really have Vi minus Vj to be on the scale of U.
I am going to play the game. That's my Ionic Hubbard model.
You're going to play with binary disorder. Okay.
I'm going to play with checkerboard potentials, which is Vi minus Vj is constant. That will give me confidence, at least for constant V, what is the scale? Yeah, exactly. Okay. You're basically preempting my talk. Good. So, okay, ABC is the following. So, all bonds, once you have, say, some potential realization, all bonds can be categorized into either A-type, B-type, or C-type bonds, where basically on the A-type bonds, the potential energy difference across this bond is kind of small, less than alpha t. So, on this bond, what you get is basically a slightly modified TJ model. Okay, some small modifications, etc., but essentially a modified TJ model with a disordered potential. If you have bonds which are B-type bonds, which means the potential energy difference across the bonds is greater than alpha t, but still not order u, you basically have no low energy hopping, you just have only second order terms. So this is in some sense your Anderson physics kicking in, with basically saying if I have very large potential energy difference, I should not be hopping across those bonds. That basic idea is getting incorporated here. And the third thing is that, however, if this becomes very large order u, then you open up new channels of hopping, because you can hop, and the potential energy cost you pay can be compensated by creating a double or annihilating a double occupancy. Okay? So this is basically the three A, B, C type bonds, and essentially if I, for example, give you a disordered potential, there is an effective Hamiltonian on each bond that you can now write down. What we will see is exactly what you were saying. We will fix Vi minus Vj to be something and look for what happens in what is called Ionic Hubbard model, and we will put it order u here. And then for the disordered superconductor, we will put random potentials which are either here or there. Okay.
So disordered superconductor will be binary disorders.
No, box potential.
Right. Oh.
Box disorder. But I can take the box width larger than alpha t, so that I would have things here as well.
I see. But you could also play the
binary. I can play the binary game where I just put randomly some v's or impure.
V has to be 0 plus u or minus u.
Yeah, v 0 or minus u, and then I place them at some random locations. You can play those games. I'll show you one data which is exactly with that model.
Okay.
Okay. Okay, so but let's first look at Ionic Hubbard model. I'll tell you what the model is. This is the work done with Abhishek. And so the model is the following. You define it on a bipartite lattice, like a 1D lattice, square lattice, or a cubic lattice. And you divide it into two sublattice, A and B. And on A and B sublattice, you put a one-body potential which is oscillating, basically. It's minus V by 2 on A sublattice and plus V by 2 on a B sublattice, let's say. Okay. Now, the reason for doing this is for every hopping across a bond, Vi minus Vj is just V, a constant, rather than a distribution. And we would first like to get an answer for what happens in this case before going to distributions and so on and so forth. Okay. So, we will study this model for u larger than t, V order u, and one particle per site. And here is basically what happens before I go into the details. The antiferromagnetic order at V equal to 0 vanishes and you get a paramagnetic insulator. And then as you change V and go closer and closer to U, you get a superconductivity of mobile double occupancies and holes in your system. So let's see how we get there. Okay, so but before that, what are we looking at? We are looking at this model where if I set U equal to interaction 0, and I look at V, as I have said, I have broken the unit cell symmetry, so it will remain a band insulator. This is a Slater, in this case, not spontaneously broken symmetry, but superlattice potential, but this will give you a non-interacting band insulator. If you set V equal to 0, go up in U, you get a Fermi liquid or a spin density wave, depending on exactly where you are, and then as you crank up U, at some point you go to this Mott insulating regime. And what we are going to look at is in this regime possible phases near V equal to U and see whether what happens to the system. Okay, motivation 2 is that we have seen in this case at 0 doping there was no charge motion. As you allow charge to fluctuate around the Mott insulator, you suddenly get superconductivity and a host of other interesting phases. This is another material which is called organics. Here things are tuned with pressure. But again, as you start allowing charge fluctuations around the Mott insulator, you start getting superconducting states. And in fact, you can ask, okay, is this kind of fait accompli? Like, does introducing charge fluctuations around the Mott insulator kind of always lead to superconductors? And is this then a good way to always think about get higher and higher temperature superconductors? Okay, so that's the kind of question you can ask here. Motivation 3 is that this is a model which, at least for 1D, was introduced in 81 by Hubbard and Torrance to study 1D charge transfer compounds like TTF chloranil. And basically above 84 Kelvin there is a neutral molecule, and below 84 Kelvin it just breaks up into TTF plus and chloranil minus, and this model was used to study that transition. It was also introduced as a possible model driving ferroelectricity in perovskite oxides like barium titanate. And motivation 3 is in cold atoms. Recently, Tillman and Slinger's group has been able to actually implement this model on a honeycomb lattice. And what you are seeing here is that they're doing spectroscopic measurements. And as U becomes close to V, you see that you get two energy scales in your problem. One is U plus V and one is U minus V. These are the energies of the double occupancies when they are sitting on the plus and the minus sublattice, A and B sublattice. And you can see that they can track all of this using their.
Sorry, Rajdeep, that was too fast.
Yeah, go ahead.
So what's the vertical axis, delta over U?
Which one?
The big one, yeah.
This one. Delta is the staggered potential, what I'm calling V.
Okay. So if delta is equal to 0, the very top plot.
Yeah, this is what we looked at way back. They're doing double usual shaking exercise. So yeah.
So they're shaking the lattice
And
and seeing at what frequency
can you get double
can
occupancies?
you generate double occupancy.
Yes. So this is u and some. But once this starts becoming finite, what you see is that you break it into two pieces. One is u plus delta and u minus delta.
Okay.
And that's because if the double occupancy is created on A sublattice, it's u minus delta. If it's created on B sublattice, it's u plus delta.
Okay. And what happens at very large delta?
Well,
Why does it go the wrong way?
Well, this I think is basically when they're going to 1.33.
The ground state already.
Yeah, ground state basically has a lot more doublons. It's at very large delta, 202020 is the ground state, so we're basically seeing the opposite way. More doublons in the ground state, and then you're destroying some of them as you are creating excitations. Okay. So what do we know about this? We are not the first to study this model. So what we see is that there's a lot of work in 2D with dynamical mean field theory, and the idea is that at least for intermediate u, which is of the order of the bandwidth, you go from a band insulator, then there is a gap closing which looks like a metal, and as you crank u up even further, you go into a Mott insulator phase. So ideally you go from band insulator to metal to Mott insulator. If you allow broken symmetries like antiferromagnetism and so on, some of this band metallic phase might get gapped because of broken symmetries.
What is V here? So it looks like you're tuning U.
This is done at a fixed V and you are tuning U. That's how they do the calculation.
And what is the V they use?
I think the V that they use is about 3T. Yeah. And we are of course interested in large U, and in this case in the 1D there is some work by Manmana and others using DMRG, and they look at the single particle spectral gap, and what they see is that the gap comes down, but even up to 512 it doesn't really close, it comes down and then basically goes up. So no metallic phase, at least I don't know whether if you do extrapolations whether this will go to 0, probably not. They seem to say that this is a finite gap here. And so the answer here is that there is no metallic phase, at least in the 1D model. Okay.
Does it matter what is the ratio of delta to T?
So when they're doing this, their delta is U 20. This was done with delta 20. This is done in the limit in which we want to look at the model, but we are going to look at 2D or 3D, but this is done with DMRG in the limit that we are looking at. Large U, large V, U order V. Okay. So what do we do? So our basic point is that, look, we know what the effective Hamiltonian is here. We are interested here. So let me just work with that effective Hamiltonian. And this has some new hopping terms because I have opened up some new channels of moving electron fermions, and ask what does this give me? What does this amount to? Okay, so remember we are doing an expansion around the V equal to U point, so no 1 over U minus V point, and this is the more standard thing that people usually do, which is around the V equal to 0 point. This you will, as you will see, will get into all sorts of resonances as V goes to U, will get invalidated. Okay, so the only point is that this is very different from doing an expansion around the V equal to 0 usual Hubbard model. We are doing an expansion around a very different limit. Okay, so how do we look at this object? What we do is we basically say, look, there are 4 states in the local Hilbert space. We will write them as spinful fermions, and there are some charged bosons with plus and minus charges. And because we are introducing more variables into our system, we need to put in some constraint to get back the physical Hilbert space. This is more like pattern construction in high energy physics and so on. And so suppose we are at near V near equal to U and we are at half filling, then what you will say immediately is, look, On B sublattice, I don't want doublons because it's U plus V. It's very high energy scale. Okay? Now, at half filling, that also means there are no vacancies on A. Suppose I have a vacancy on A. I would rather put it on a B sublattice and gain the potential energy, which is also order U. So, unless I am having a lot of vacancies which cannot be accommodated by in the B sublattice, in general, I would basically have the following projection that no doublons on B, no holes on A, okay, which is different from the saying just no doublons, period. Okay, so that leads to formally these manipulations, and hence the constraints also look very different at half filling. So these are the objects with which we are going to construct the theory.
So what are the C operators?
The original fermion operators. I mean, if you're thinking electrons, then electron operators.
So to create an electron, I have to destroy the hole
and create
the F-type fermion.
F-type fermion, or if I want to create it on B sublattice, then I have to first create a double occupancy and annihilate the other kind of spin. That will give me, suppose I want to upspin, I first think of creating a double occupancy and then I basically annihilate a downspin. That will give me a upspin.
So the operators on A and B sublattice are different?
Yes, in terms of these objects, because of the projection. I can start with a common operator, then use this projection to make these operators very different. And if you're wondering where this sigma is coming from, this is required to keep the anti-commutation relation of original fermions. Otherwise, you would be doing some very weird transformations. Yeah.
So I'm a bit puzzled. On B, there are no double occupancies.
Yes.
So why do you need to create a double O? Oh.
I don't create it. So sorry. This I think has been. This should have been B. This should have been A. Sorry.
What are the indices?
So let me write it down. C dagger A should have been sigma. Should have been F A sigma bar D dagger A, and C dagger B sigma. This is the correct transformation. Sorry, there's a typo there. Don't look at that. You will get confused more.
Okay, easier now.
Okay, sorry. Thanks for pointing that out. Yeah. Okay. Now, with all of this, you can ask, what is the effective Hamiltonian? I have just been writing all these operators. I mean, what is the effective Hamiltonian? The effective Hamiltonian has now two main parts. The first part is that for creating a double occupancy, I pay a cost U minus V. I can only create them on one sublattice, and I can pay a cost U minus V. Okay? So that's like a fugacity term or a chemical potential term for the doublons. Okay? And the second term is the additional low energy hopping that I have created, and this looks like the following. It looks as if you are taking a spin singlet on a bond and converting it into a 2-0 and the reverse process. So you can move the upspin or the downspin. In this language, you will basically see that you get an overall phase between them. So in the end, it turns out that this you can effectively think of as if you had a spin singlet on a bond. This just moves and creates a 2-0 on a bond and then comes back. So this is the process. Okay, this is what we call the dimer dipole model, because when I create a 2-0, it's a local dipole, and the other is a singlet dimer model in this case. Okay, plus you have a bunch of other terms which I'm not going to tell you in details about, but they are not the one which governs the physics of this. I mean, constraints are important to keep, but so then we do a mean field theory with this. Okay, this suggests that there should be a singlet amplitude. This suggests that there should be a doublon hole pairing amplitude. It's a natural mean field of objects to give. we know there is antiferromagnetism in some limits, so we put in antiferromagnetic pairing. These are bosons, so in principle they can condense, so you need to allow for a condensation if it happens. Okay? So that's the condensate, double honor hole condensate. And then you just do the mean field theory. Well, in reality you have a bunch of other mean field parameters and so on, but let's say you just do the mean field theory with this. Here's the answer of what happens. Now, the theory here you should not trust too much, okay? But okay, I mean if it was giving me something very weird, not an antiferromagnet, I would not trust this theory because, okay, U is 20 and this is 10, so this is V minus U order U by 2. So, but anyway, things start happening here is that the antiferromagnetic insulator, the antiferromagnetism starts vanishing. Okay? Now you can ask what is the state I go to. The state I go to is that there is a finite double hole pairing, but there is no condensate of double ends. Okay? So it's a state of local fluctuating dipoles. I'll come to a description of the state soon. But if you increase V further, what you see is at some point the individual doublons and holes condense, the single particle gap vanishes, and this is the condensate fraction, and this is what I am going to call a superconductor. I'll tell you why I am calling it a superconductor slightly later. Okay, so the fact that you have constraint actually forces the condensation of doublons and holes. I mean, you might think, why are we getting a condensation? The number is not conserved, but there's a constraint acting on them. That's what's forcing the.
If I remember correctly, in the state boson representation, there is this gauge symmetry.
Yes.
And the constraint actually
the Lagrange multipliers are become the gauge fields. Yes.
So it's important to keep that constraint.
Yes. This here the constraint is kept on average, so it's like a saddle point. Its fluctuations will give you the gauge degrees of freedom to look at, and I will comment on what happens to the gauge degrees of freedom, but I will not spend a lot of time. I can talk to you later, but I'll tell you basically what happens to the gauge degrees of freedom. You're right. Once you let the Lagrange multipliers fluctuate, that's what gives you gauge fields essentially. Okay, so you can do it on square lattice, on a cubic lattice. In a cubic lattice, the paramagnetic insulating phase shrinks, and there is some first order transition from antiferromagnetic superconductor. And basically, but you get a very similar sort of phase diagram, only things are shifted around in the 2D versus 3D case. And then you can ask, okay, so these are kind of just, I just gave you some expectation values and so on. What is the picture? What is happening in the system? Here's what is happening. See, as V increases, you're basically lowering the cost of creating doublons and holes. So you would create doublons and holes. Once you do that, the kinetic energy prefers singlets rather than Néel ordering. Okay? So the Néel ordering starts going down and it vanishes because it would rather like to create local singlets like this. Okay? So you get local double hole pairs, but these are charge neutral objects. You have to understand that they're created in pairs. So overall there is no additional charge moving around in the system. So in some ways you can think of it as a superfluid of neutral pairs, doesn't carry any current, and this is the paramagnetic insulators. And that's what is happening. So if
so wait, to be a superfluid, you have to have some long range of diagonal order.
Yeah.
So what is
D dagger, H dagger, DH. D dagger, H dagger on this bond, DH on this bond. Sum of diagonal long range will be finite. In a way, you're not going to measure it because there's no. The way to measure superfluidity would be to actually couple U1 field to it.
Can I measure it with an interference experiment?
I'll tell you what you can measure it with. Just give me a few slides and I'll come to that question. You can see signatures of things, but not quite phase coherence in this way. I mean, if you had a gauge field which couples to that, if you had a U1 field, you can ask what the vortex looks like. that would be give you idea what what do I mean by superfluid. And the vortex would be a whole current and a double-on current running in the same direction. So overall, it's just no current. I would not see anything there. In fact, David, just to come back to that question about gauge fields, technically at the main field level, this would be a deconfined gauge configuration, but again, it's mean field. In 2D instanton processes will probably confine it. So I'm not going into details of those, but that's the state.
I don't understand. Double-on has charge 2, all has charge 0.
Oh, I'm measuring from the uniform case where there is charge 1 on every side.
Okay.
But it doesn't matter overall. It's the fluctuations of charge that matter. So essentially, you can take the 0 of the charge anywhere.
So if these were charged particles, this would be a charge-neutral object.
Yes. I mean, you measure the charge in terms of the fluctuation from the average density, right? So from the average density, the fluctuation is plus or minus. That's the point. Okay, so but what is the dynamics? The dynamics is the following. You create a 2, 0, but you don't have too many 2 zeros before anything happens. You just fluctuate back to a singlet, 2, 0, singlet. So you basically have local fluctuations, but the charge doesn't delocalize. Okay, that's why it's an insulator. In the next case, what you can ask is, but what happens in the superconducting phase? Now remember, I have increased V a little bit more. The cost of creating double-on hole pairs has gone down, so they are more abundant now. And now the following thing can happen. Let's see, suppose I have fluctuated to a 2, 0. Before it goes back to the singlet, something else fluctuates to a 2, 0, nearby side. Okay? Then these two will fluctuate back to can fluctuate back to a singlet, and you have delocalized the 2 and the 0. Now you can keep doing this, you can keep doing this, and you can keep on delocalizing the charge. All the processes are low energy processes. There is no virtual high energy process involved in this case at all.
So in the previous phase, can the singlet bonds rotate?
What do you mean by singlet bonds rotate?
So you're drawing singlet bonds.
Yeah, they can rotate.
Right. So to like whatever fourth order in
Yeah, but I am giving you a first order in T term. I mean, okay, if you are saying that the fourth order in T cube over U is going to compete with that, then I don't know.
Second order.
No, not second order, it will be fourth order. You're talking of the Wilson loop term, right, which is basically going to, but that's, in this case at least, would seem, I don't know. It would seem that
it's not going to make resonance valence bonds either.
I mean, the paramagnetic phase, it might, but see, if you think in the dimer model language, the fact that you can create the 2 zeros is like a monomer term. Monomer terms are always relevant in RG sense. So it will take you away from that. Now, whether in between you can really get a phase, Polyakov will tell you probably no in 2D. I don't see there are no gapless excitations around to couple to. At least that's a question which is way beyond mean field theory. You should not trust any mean field answers for that.
So paired superfluid is supposed to be gapped.
Yeah. Single particle excitations are all gapped.
And two particles.
Two particle is also gapped. It's like my bosons are gapped.
And what happens between antiferromagnet and paired superfluid? Does one of the gaps close, or it's
Okay.
remains
So
gapped?
it remains gap. Basically, what happens is a weakly first order transition. So the gap is coming down. It looks like it will almost close. It's preempted by a first order transition to another state, which is again gapped. So it's not.
And should I trust mean field on this?
I think if you get second order transitions, you may not be able to trans mean field. I mean, if you are getting first order even in mean field, it's, well, you can always add some other term to basically smoothen it and so on. I don't know. Sure. But I would, yeah.
And the Nonmonotonic calculation, where is it on this axis?
It's basically Nonmonotonic calculation would be somewhere here. It's 1D.
So, but does he sweep from anti-Fermionic to superconductor?
Yeah, he doesn't know. He have not looked for superconductivity. He has just looked for gap, but he does sweep from antiferromagnetism away from the non-antiferromagnetic states.
I see.
Okay. And I'll give you an argument why in 1D you may not see the superconductor here. Let's just go through this. Okay, so see, a single double-on or a single holon actually is charged with respect to even the EM field. Okay, so it's low charge condensate with respect to electromagnetic field, and so that leads to superconductivity. What you can do is use the current correlators to calculate the superfluid stiffness, and the answer is proportional to the condensate fraction, which is not surprising, and proportional to the singlet amplitude, because you need to have singlets to be able to fluctuate and go through this process of delocalization. Okay. Now, this 2z minus 4 will tell you that even in the main field in 1D, you're basically setting it to 0.
Z is number of
coordination number. Okay. Why, we can probably discuss later. I have an explanation, but let's not get into the. So 1D, it may not be useful to compare. That's the point. Okay. So what happens is that since it's proportional to phi square and C1, phi square of course increases as a function of V. C1, number of singlets go down, and so the whole thing looks like a non-monotonic dependence on V, and it reminds you of kind of high Tc, where this is again a non-monotonic dependence of Tc on some parameter, and in this case dominated by vanishing of the order parameter, and in this case dominated by vanishing of the stiffness.
So for 2D I can understand why stiffness is related to Tc. But what about 3D?
Okay. What about 3D?
Well, in 3D I should also think about single fermion excitations.
Yes.
Which is not a part of the stiffness.
No, but they're gapped. So it's a question of whether that gap vanishes first or the stiffness vanishes first.
That's right.
Yeah, and we have done finite temperature calculations to see that the stiffness vanishes first.
Oh.
Yeah, so things are gapped. And which also means when you go above that, you are going to go and land in a gap phase, some sort of a quote-unquote pseudo gap physics will come about. We have looked at the single particle spectral function. This is what you were talking about. And the gap is sum of the gap of the bosonic gap and the fermionic gap. In the low V regime, it's dominated by the bosonic gap because it's just the fact that you pay a lot of energy cost to creating them. It's like a mass. The mass of the bosons vanish at some point, and then they remain 0 in the superfluid phase, superconducting phase. Here the fermionic gap is ordered J. You can't really see it because it's ordered J. But here it kind of takes off. So basically the total gap looks like this. Here dominated by the boson gap, here it's dominated by the fermion gap, here spinon gap, and in between, as I showed you, that it doesn't really go to 0 because it gets preempted by a first order transition. Okay?
So where is the superfluid phase and where is the superconducting phase on the speed scale?
Okay, so the superconducting phase is here.
Okay, cool.
Superfluid, paired superfluid is somewhere here. Small, much smaller region.
And I have to add up the fermion and the boson gap because of the slave particles.
Yeah. I mean, one way to think of this is that in terms of this is like a polarization function made out of one boson line and one fermion line. So that's basically what it will look like. Okay, so if you measure the single particle spectral function, what you see is that in the paramagnetic phase, you have gapped but very incoherent spectral weight. There's no nice quasi-particles sitting there. Okay? Whereas as soon as you go superconducting, you basically the condensate forces you to have very sharp quasi-particle peaks. So for example, this could be one way you can distinguish these two phases. Okay? And to answer your question, Daniel, basically once I'm in the superconducting phase, once the bosons have condensed, then the gauge fields are Higgsed out. Then I don't need to, so I'm much, stronger footing talking about the superconductor than about what exactly happens in the paramagnetic insulator, where the low energy excitations around this would be dominated by the gauge fields.
So to be precise, here you're getting superconductivity from a potential which goes like this and repulsive interaction.
Yes, combination of these two. So the delocalize. Okay, so the other way of, a very cold atomish way of thinking about it is, people can make these parity measurements locally. So a doublon is a 2 and a holon is a 0, which both shows up as, I guess, black, and the single sites, let's say, show up as bright. Okay, so if you are in the paramagnetic insulator phase, whenever you get dark sites, you should get them in pairs. In the superconducting phase, single 2s and 0s kind of proliferate, so you should see more single particle states, single dark sites with no other dark sites on its neighboring sites. Okay, so the statistics would start changing in this way. Okay, how much time do I have? Should I go, or should I just?
10 minutes.
Minus 10 minutes. So maybe then I do not talk about the second, or maybe just without telling you how we do it, maybe just I tell you what are the results.
So I would love to hear, but I think we should
Okay. So that I can
ask the audience if they have any questions.
Yeah, okay. So I can stop here. I mean, this is a good point to stop if you